check out this ginormous rock. It is 0.3 metres across. Now actually this is almost identical to these grains of sand, but the major difference is, of course, the scale. If we trap a grain of sand in this micrometer, which I've done here, you can see that this is 0.3 millimetres across, meaning that these grains of sand are 1,000 times smaller than this rock. Let's have a look at them under the microscope. So here we have that sand under the microscope. And what you can see is that it looks exactly the same as the big rock. We've zoomed in so that our sand, 1,000 times smaller, is now, well, looks to us the same size as the big rock, and it's not changed. But how far do you have to zoom in before things start to look differently? At some point, our microscope will not let us see smaller. But what we can infer from other experiments is that things do change when we get really, really small. The atomic hypothesis, the idea that structures and everything around us is made out of atoms, is a very old one. But now we've formed a very consistent understanding. If we took our rock and we went 1,000 times smaller, we would get our grain of sand. And if we went 1,000 times smaller, we would see the individual silicon dioxide crystals that make it up. And it's only when we go 1,000 times smaller than that would we see the actual atomic structures making up the giant covalent structure of the silicon dioxide crystal. That is a difference of about 1 billion, which is 10 to the 9. The radius of each of these atoms is about 1 times 10 to the minus 10 meters. Now that means that if we had a rock that was 1 meter, it's 10,000 times smaller. So here we have it, zoomed in to one of these oxygen atoms. Well, what are we going to see? The first thing I want to add to this diagram is the scale. The radius, so from the midpoint to the outside edge, which I'm going to draw just here. This scale is 1 times 10 to the minus 10 meters. And if you're not used to standard form, that's the same as saying 0. meters. A very small distance. But that's not where the structure ends. Because if we voyage deep inside the atom, we can see that the atom itself has some structure. Here in this field, 500 meters across, we can get a good visualization for the structure inside the atom. If we imagine our atom was this big, then here, 10,000 times smaller, would be the nucleus of the atom. The place where most of the mass of the atom is concentrated at the center. Now this isn't the only thing in the atom, because if I'm right, there's something way over there as well. And here it is, the electron. Around this atom, around the nucleus, there are 8 of these for oxygen. These carry the negative charge, and they sit in all of this empty space outside of the nucleus. The nucleus of the atom and the electron around the outside. Of course, we can't draw a diagram the size of a school field. So we draw a diagram that is not a scale diagram, but that represents the structure within an atom. And here it is. You can see the nucleus in the centre and the electrons in that empty space around the outside. But notice in this diagram, I've drawn it realistic into how it would look on this model. This is a spherical object, and though there are 8 of each colour, you can see that you can't always see all 8 because some are behind each other. And so this here, I think we should change, squash it out so that we can directly count how many of each of these particles are in the nucleus. So let's do that. So there we have it. Now we need to name these things. The first ones I want to name are the red subatomic particles, and they are called protons. Protons carry a positive charge. And here there are 8 of them. In blue we have 8 neutrons, and these are neutral. So these have no charge whatsoever. It means that with 8 positive charges and 8 neutral charges, the overall charge of the nucleus is positive. Around the outside, in this atom, we have 8 electrons. And these have a negative charge. Being 8 in total and all having 1 negative charge each, they completely cancel out with the positive charge at the centre of the atom, making the whole atom electrically neutral. Now, before we look at the nucleus in detail, let's take a look at those electrons. Now, from chemistry, we learn that the electrons are not just randomly distributed, that the electrons are most probably located in various areas, with 2 electrons found close in and further electrons further out. This gives a rise to the electron shell structure, with 2 being in the first shell and for oxygen 6 being in the next shell. Now, what can happen to an electron in this shell structure is it can move positions if it is given energy. So in the movement of position, if it is given just the right amount of energy for a transition from one allowed state to another allowed state, then it will absorb that energy that has given it that promotion. What will happen though, it will go back down to that lower energy state again and give off that same energy again. Now we can see this because what we can do is we can shine light onto some atoms, and when the electrons get promoted, they will absorb the light that is equal to the energy difference between here and there in those different positions. We don't have to form a complete understanding of this in this topic. What we do need to know is that the electrons moving from one energy state around the nucleus to another, akin to moving positions, results in it absorbing light when it gets promoted. Here we have sodium vapour illuminating what is sodium chloride and alcohol solution. What's happening is this is burning, and so what's happening is it's making the sodium ions airborne, where they can then absorb the light that is coming from this here. Now the sodium light is producing light at exactly the right energy to be absorbed by the electrons in the airborne sodium atoms over here. Now what also will happen is that this same light will be given off when those electrons move back again. And it is that which is making the sodium light work. So here we have absorption and emission by the shifting of energy states of the electron. So what was happening there? Well, what was happening was that light of a very particular energy was coming into the atom, and it was being absorbed by this electron, which gave that electron enough energy to move positions to somewhere else. In that process, the light, which everywhere else will carry on, was absorbed and so has gone. And that is why that flame appeared black. What will eventually happen is that electron will go back again to its original position and give off that light once more, but in a random direction. And so that is why we see the fire glowing in other directions, but black when you look at it along the original line of sight of the light. For our atom, we can characterise what it's like with the following notation. First of all, this is oxygen. And so we would use the chemical symbol for oxygen, O, like this. And we could represent this as a tile on the periodic table. What we would have to put on the left-hand side towards the top is the atomic number. And here, the atomic number is 8. Now this represents the number of protons, or the number of positive charges in this atom. It is, consequently, also equal to the number of electrons in this neutral atom. And so, therefore, it also tells you where in the periodic table it is going to appear. 8 protons means that this is actually, if you take hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, this is going to be group 6. At the bottom, we have something known as the mass number. And this is telling us about the total number of protons and neutrons in that nucleus. There are 8 protons and 8 neutrons. So in total, we can get 16. Now, any substance I might have can be represented with notation like this, and you will see it on a periodic table. Changing the number of protons changes which element you are. Now these two samples of water look exactly the same. The chemical properties are identical. This is water, so is this. But there's something different about these. When I put this one on the scales, it is 72.3 grams. This one, 72.6 grams. There is a slight difference in how much each of these weighs, in that this one has more mass. And this one is in fact heavy water. Some of the hydrogen atoms in the water molecules are not like every other hydrogen atom. Some of the hydrogens in here are paired with a neutron, which we don't normally get with hydrogen. Having an additional neutron makes some of these atoms heavier, and so the whole thing is heavier, but indistinguishable in every other way. The hydrogens that have that additional neutron, well, they are called isotopes of hydrogen. Here, the nucleus of the atom is represented as 2 colours of plasticine balls. So there's the reds that represent the protons and the blues that represent the neutrons. In this oxygen nucleus, they're equal, there's 8 of each. But what happens if I had one less neutron? Then what I've basically now done is created a different isotope. It's still oxygen because it still has 8 protons and 8 electrons, but it's a different isotope because it now only has 7 neutrons. Alternatively, I could get an additional neutron and stick that on as well. So now it has 9 neutrons, still oxygen, just a different isotope. What would happen if we lost one of these electrons? What if it was given so much energy that the electron completely departed from this atom and was now external, cast away? Well, now you would notice there is only 7, and rubbing this one out because I've drawn it twice, there are now only 7 electrons around this nucleus, with 8 protons and 7 electrons. there's no longer that balance of charge. There's now more positive charge than negative charge. This whole thing has become charged by 1, where 1 is the amount of charge that a proton would hold. This whole atom, if it has gained a charge, is given a new name. We call it an ion. An additional way that an ion could form, putting that electron back in, is if this atom gained an additional electron from somewhere else. And now it has 9 electrons, but still only 8 protons. It has a net charge of -1. This is also called an ion, and we can prove that they exist. So check out this. I've got distilled water in this beaker, and I've got 2 metal electrodes connected to either end of a battery. There's an ammeter in the circuit as well, and what we can see is with that distilled water in there, there's no current flowing through this circuit. Now, ions, so charged atoms, are going to have charge just like an electron would, and when placed in the potential difference of this battery should start to move just as electrons would. So let's have a look. If we get some ions and chuck them in, do we see an electrical current flowing through this circuit? Well, let's chuck some in. Ta-da! There you go. Now ions are are moving through this water, proving that they exist. In summary, if we have 2 atoms and they have a different number of protons, then these 2 atoms are different elements. And that is what's displayed in the periodic table. If they have the same number of protons, but different numbers of neutrons, then these are isotopes. If they have the same number of protons and neutrons, but differ only in the number of electrons they have, then they are different ions. Now, careful here. Generally, the neutral atom is just called an atom. It is only when it is either missing or has gained an electron that it becomes an ion, because ion really means that it is now charged. You need to be able to use all 3 of these words in the correct context.